Okay, we're live. Let me see. Okay, I'm gonna assume this stream is recording. So I am gonna do a little bit of coding. And this effort is gonna be. I'm gonna try to make a visualization of the state of a program. And this is part of the effort of the time traveling debugger, which I had talked about in previous videos. I'm actually gonna grab that video out of my channel. Oh, there's the play programming language, which I believe has a link to that. So I'm gonna program language. I don't know if this finds the play framework is not what I'm talking about. Okay. I had the fun language and the play language. Yeah, this is it. So it makes sense. Nobody really knows about this programming language. So the play programming language is something that I've been working on. Its primary purpose is is an experimental playground for a concept that I've been kind of obsessed about, and that is the time traveling debugger. If you want to learn more about it, if you've not been introduced, then you can watch one of these videos. Probably the best intro is the dream of the time machine. So right now I'm gonna do some work to try to push that idea forward, but I want to give some preface before we start. Okay, so I've been thinking a lot about what this time machine is going to be like, and there's a lot of uncertainty, but it is guided by a huge part of the inspiration for this work is Brett Victor's work. Brett Victor is one of his most famous speeches was Inventing on Principle, and in there, well, so you can watch this talk if you have not done it yet. I highly recommend it. You will not regret watching this talk. But one of the things that he really harps on is the idea that the visual aspect, the visualization, the ability to see what you're doing is extremely important for the creator. You can think about programmers as creatives, and the less they can actually see what they do, the less they're able to do productive work. And this effort is all about that. So, and one of the things that let me see, in there somewhere he has this part about seeing how an algorithm works. There's this part where where you can walk backwards in time in the execution of a video game, and I think I showed this part in the Dream of the Time Machine. So you can go ahead and watch that, but the part I want to show is actually this one, where he writes a binary search, and on the right hand side, it there's an aid to tell you what the algorithm is doing, kind of. So you can you can either, or you can both define what the variables are supposed to be, and it'll execute the algorithm and show you what the concrete values of the variables are at any given moment. And the thing I think that's different in this visualization, the thing about it that's different from a normal debugger, is that this is not a stepping back and forth in time kind of user interface. There's no step debugger here. There's no like current line here. But instead, as this loop loops, each iteration of the loop is rendered in a separate column. So this is iteration 1, and this is iteration 2, etc. And when there are many iterations of the algorithm, you actually get more and more columns, and that could become problematic when there are like hundreds of columns. If you have a loop that loops hundreds of times, and how are you going to visualize that? That's going to start becoming hard to see. And his thing is just a prototype. But I have a more ambitious goal of making this thing actually practical. And also, he has not answered the question of what happens if your code calls into another function, and then there's a this drill down aspect. You either want to drill into what the subroutine has done or not. And he didn't give us an example of how to handle that. Now another inspiration that I take. There's several inspirations I take. Another one is the concept of zooming. I've done a lot of learning about fractal geometry and Benoit Mandelbrot's work in particular. And one of those things, I did a video recently on. Sorry, this is like meandering, but that's sort of expected when you're on a live stream. Oh, hi. So, Hamid Ajel, I actually have someone visiting this stream. I am sorry if I'm mispronouncing your name. So he's been watching some of my programming language videos. I actually don't mind answering some of his questions. He's asking me, how do you generate source code from AST? Oh, are you talking about if you given an AST, you want to generate like in the reverse direction? Like you wanna see, you have an AST tree and then you want to generate JavaScript? Is that what you're wanting? Are you asking about code generation? So for code generation, admittedly, I haven't gone into a lot of detail about this. I don't know if he's still watching, but I'll try to answer this question quickly, if I can. Okay. I don't know. I don't know if I can. Okay, this is my channel. Oh, actually, I think going to tobyho.com is a faster way to do this instead of going to YouTube. Okay, code generation. How to build a code generator. So I did cover this, though not in a very in-depth way. But I'll copy this link. So I'm gonna try to answer his question here. That video covers code generation. That's the process of taking AST and generating code. In this case, JS code. I also have a video earlier than that about the very first video in this language, where I talk about what does it mean to make a programming language, I believe, and I explain if you need context about what code generation means. So he says, I've made a programming language and a parser generator, and I want to make a source-to-source compiler. Right. Code generation, which is the last step. It generates or whatever host language, or whatever target language, I should say. So he's saying we have some communication issue. Oh, my YouTube is not receiving enough videos to have a smooth stream, apparently. That's sad. I don't think the frame rate is good enough at the moment. I'm not sure. I'm streaming the kilobytes per second. Okay, it's good again, I guess. Not sure. So yeah, so it seems like we have a very motivated individual who wants to learn how to make programming languages. Oh, he's been emailing me and I haven't replied. Sorry about that. Sometimes I get behind. Check the date. Okay. Okay, so yeah, so okay, so I hope I have helped him on his way. I was planning on working on this deep zoom debugger, but yeah, I had a viewer asking me questions, and I don't mind asking him. I think he's gonna watch my video on code generation, how to take AST and generate JavaScript. I hope that helps him, but then um, if not, then I will try to help him more. Okay, so I'm going to try to continue this work here. Okay, so I was talking about Brett Victor, and and I made a video a little bit ago. Although I haven't put it up on my website yet, but I could. Um, so that one was called the Deep Zoom, like the Google Earth like zooming viewer. That was this one, Google Earth like zooming file explorer. So there I made a user interface that works sort of like Google Earth, but for the file system. Let me see if I can show it. Oh yeah, here. Yeah. Okay, so this is like a visualization of the file system, and with it you can zoom in to a directory for files, and then you can zoom in even more. Like you can zoom into this node modules, and then even more into a specific node module, and even zoom in close enough to see individual files. Yeah, so this, like, you can zoom into a particular subdirectory, and you can even zoom into a file, and then you can read the text inside the file. So this idea of the multi-level zooming is something I want to use. And other than that, another source of inspiration is the Chrome profiler, which I'm also gonna show off, I believe. So let's say, let me open up my text editor here. Oops, this text is extremely large. Okay, so I did just a little bit of prototype work on this a few weeks ago, and I guess I'm gonna try to pick it up now. But let me spin this thing up. Okay. Okay, so I'm using a canvas-based user interface here. In currently, it just prints out a line of code. But what I want to say is that this CPU profiler inside the Chrome Dev Tools is another source of inspiration. So if you record the execution of the program and then you do something and then you stop recording, it sort of traces everything that the program does and it renders it in this manner. First, there's this CPU graph here. So this guy is, well, this whole thing, not just this chunk, not just this chunk with the yellow in it, but really this whole thing from the beginning. This is a CPU utilization graph. So CPU utilization graph, and if this is pegged, if the graph is up here, that's 100%, which means the CPU is pegged is at 100% utilization. Here it's at 0% utilization. Okay, so there's this part here when the CPU is being used the most, and that's useful information. It tells you where your program is being slow, but it gives you more. There's more. In particular, you can drill down to and figure out what's actually happening during this time window. So you can like zoom in and like select that range, and then this gives you the code breakdown of what JavaScript code. Yellow means JavaScript code execution, by the way, whereas blue means rendering engine execution. That's like the CSS engine has to do work to update the display. Oh, actually no. Blue is parsing of HTML. I believe purple is CSS rendering engine execution. But anyway, most of it is yellow right now, and you can, because it's yellow is JavaScript execution, you can drill into the JavaScript execution to figure out what code is actually happening, and therefore what code might be slow. And in my case, and this is like a Google Earth kind of zooming interface where you use the mouse scroll wheel or this two finger, basically the mouse scroll wheel to zoom in and out, and you can zoom really in. And I have seen this, I know what this code is. This is nearly.js basically. This column.process is code inside nearly.js, as is this parser.feed. So this parse function is taking 17 milliseconds, which isn't that bad. Wait, is it that bad? It's actually kind of bad. The step function is taking 1.21 seconds total. So that's actually a little bad. And that spans across from here to here. There's some stuff that Webpack is doing that's taking 180 milliseconds, and that's fine. The parsing of the HTML is taking 345 seconds. But I would say the main point of interest in this case is the parser. The parsing of I think this is the parser that I wrote using the nearly.js tool, or well, I didn't. Mostly it's nearly.js doing the work, but the file I have is, or the code I have, if I can open it, is this. It's grabbing. I published the playlang into an npm module at some point so that I can use its parser and its traverser in a separate project, which that's this guy. So this parser, I'm gonna call this parse at some point, and that's that, and that is this. Okay, so this is the parse function, and that's the thing that's being the slowest of all in all of this chunk. It's probably taking from here to here, and that accounts for 1.19 seconds to parse this program. And the program is this, which is not a very complex program. So which begs the question, what is slow about it. But that's really not the point of why I'm showing you this right now. The point I'm showing you this is I want to show you the user interface of this CPU profiler. This is called a flame graph, and you can zoom arbitrarily deep inside here to see very low level of detail. And we can see calls to parser.feed are being made here. Calls to column.process is being made. If we zoom all the way in, we can see this thing at different levels of detail. You can see it at this level of detail, or you could see it at this level of detail, which in a sense is really kind of like this very deep zooming kind of deal, like Google Earth. And another thing that's really cool about this is you can turn on screenshots, which I have, it looks like. And with screenshots on, you can actually see what the screen looked like at various points in the execution. So right now, okay. So here, well, I guess I refreshed the page at some point. So at this point, it was still the previous page before refresh, and then I refreshed it. And now we have a blank screen, and then it's doing all this code, parse, and then finally it draws this text on the screen, this. And by hovering over this timeline, you can see the different states of the screen at any given moment, and you can coincide it with the actual execution of the program. And that's a very, very cool concept. So I want to implement something sort of like this in a way. I'm not totally sure that I want to, like the user interface, I'm not sure I want it to be just like this. This uses a horizontal timeline approach. I'm thinking maybe I do a vertical thing, and then but I want to get into even more detail than this, because I want to get into the level of detail of having lines of code in here. Like if you zoom in low enough, you can actually see individual lines of code, and also be able to see the state of the program during that time when it's executing those lines. I want to get all the way down to that kind of detail, which is possible with the way I've captured the programming state. So that's what I'm trying to do. That's a very, very long preface. I hope I can start on some work, and I'm actually going to try to, let me think, what should be the first thing I do here. So currently I have this code that is like picking the what is it even doing? It's calling render. It's just going through the history and printing the lines of code where the stack length is 1. So, and I think if I were to explain to you what I'm doing, I should probably go back to the beginning. Instead of rendering, so I printed the AST, but I'm gonna print out the history object and show you what that is. So a history file is a trace of a program, so that has the entire history of the execution of that program. I think I should actually go to the playlang repo, I believe, and show you how that works actually, because otherwise nobody will understand what I'm trying to do, is my fear. let's see here. So I think I've been using this guy, and right now we're looking at this to-do JS. Let me just open this test file, which is supposed to do this. Oh, I think I did a to-do MVC. let me do the to-do MVC one, because that looks better. Or not. I thought it would look better. Oh. There's a to-do MVC one HTML. There. Wow, that actually looks quite good. So this is the to-do MVC program, and if we clicked on debug, then we get this debugger. This is a post-mortem debugger. You can step backwards in time, like so. It's sort of like a normal debugger where it can go back and forth in time. Like if we went here, next line, and so forth. Now it's creating the various DOM elements. It's creating a key press listener now, etc. Now it's setting text. It's appending the various DOM elements. And finally, it appends everything to the body, and there it is. There's the entire user interface, but it's not done. It has to create more DOM elements and so forth. So this is the current version of the time traveling debugger that can let you walk backwards and forward in time. And as you can see this frame information. This will change as you go backwards and forwards in time. You can see the intermediate states of the program. Now, where was I going with this? And then the way this stuff works is it's based on this this history object, or this history array, which each entry of the array contains the state of the program at that point in time. So let me show you this history array. Okay, currently it has 91 entries, so that means this program has had 91 different states. And there's a line number, like which line were you on during that time. There's a stack, which is your function execution stack. Each frame, the stack contains a number of frames. You can think of it as have one frame, and that's the main function, and it can have variables in it, but at the beginning it doesn't. There are closures. We went through the process of adding closure support, and this is sort of the aftermath of that. So there's the variables within the main function will make use of a closure, and the closure is actually stored in the heap, which is over here. So this is saying we're using the object ID number 5 as the closure, which currently is an empty object, but later on it gets filled up with stuff. So this is the kind of data structure that we're working with in the history, and so forth. So this is the second entry, and its heap will have modified, as in here you can see the heap, the closure that's referenced here, number 5, actually has an entry in it as to-dos, which points to object number 7, which is an array with 6 in it, and the 6 is this item called water the plant, and so forth. Okay, so this is what the history looks like, and that's what's driving this debugger, which can walk back and forth in time. We're gonna use this though. I want to create a different rendering of the debugger, which is uses this deep zoom concept, and we don't have to do this stepping. It's just a different paradigm of how you visualize the state of the program, and we don't even need a step debugger. That's the idea. And perhaps I should draw out what I'm thinking of because I have this picture in my head. I'm not sure if the viewer understands what I'm thinking. So let's say there's a timeline, and now the it's sort of like the performance debugger that we see here. So there's a timeline. I'm gonna do the timeline vertically. So perhaps this is the timeline. So this is the time going down this way. And I kind of want to say, well, maybe each point in time, or I'm gonna plot the execution of the program on this timeline, similar to how this one does it. So maybe from this point in time to this point in time, the program spent all its time executing code in the main function, and perhaps there's a click at some point later in time. A click event happened, and as a result of the click event, we call this onClick function, and that function executed from this point in time until this point in time. Now this time unit, it doesn't necessarily have to be in seconds. It could be in terms of the number of ticks. You don't know. So now when you zoom in to this visualization, maybe like you're zooming into the main function to see the details that happen in the main function, then this main function box would enlarge, right? You're zooming into it, and as you're zooming closer and closer into it, at some point more details will emerge, and you'll see like the actual lines of code within that main function. Maybe there's a while loop in here. There's some variables getting declared while true. The play language uses square brackets, and then maybe there's some, there's a I++ maybe at some point, although that's not a valid syntax, but I'll write I equals I+1 maybe, and then there's another function called maybe x is I plus x, I don't know, and then you call some other function another fun with x, like that. So now you can see the details of the stuff inside the main function, and this is all inside the main function. Well, maybe what we do is we leave the signature of the main function, def main. So you can see this, but on the side, so to copy Brett Victor's idea of, well, how about you can just see the concrete values on the side? Maybe we do allow the concrete values on the side to be seen here. So maybe I can see that this is I, but here x, x maybe is 0. So x is a 0, and here x is gonna still be 0 because we did a 0 plus 0, but here I is gonna be 1, and so forth. We may need a second column, so to follow Brett Victor's lead here, and then the next iteration x is going to be 1 and so forth. And then maybe another function, this may or may not return a value. If it did return a value, it can show the return value of this function. But if you zoom even into this function, then we would be able to see the details of the code within this function as well. Yeah, so we zoom towards another function, then we blow the details of another function up the same way we've done for the main function, and so forth. So that's the idea. I'm not totally sure how I want to handle loops, because if I just say add more columns on the side for a while loop, again, if the while loop executes hundreds of times, well, there's going to be too many columns. It's not very easy to see. So another idea would be, instead of adding columns for the same while loop, maybe it's not, maybe we unroll the loop. So maybe it's more like x equals I plus x. Then it's gonna show like, oh, on this turn x is 1, let's say, and then some function, I don't know, and then I plus or I equals I plus 1, and then it's gonna go back up to reevaluate that part. So maybe instead of closing the loop, maybe we don't. We say I'm gonna unroll the loop and display the first line of the loop again and reevaluate this true. Well, this is always true. Oh, this is gonna be an infinite loop. And then we're gonna display the next line again. And then this time, well, I is gonna be 2 in this case, and then x is gonna be 3 in this case. And then we're gonna basically unrolling the loop, repeating every line in the body of the loop over and over again until it stops. And with a zooming based interface, this is not necessarily gonna be messy, because the user can just pan the interface to see the rest of the iterations, and he can, only look at the bits that he's interested in. And if there's if he wants to zoom into a particular call of some function, he can zoom into this one versus zoom into this one. Each one is a different execution of that same function, so with the same x value at that point. And you can, this way you can sort of read from top to bottom, and you can trace these values as they're changing. You can see the values updating on the side, instead of having to have like a separate window, as is the case with this kind of user interface. You're always having to monitor the value on the side while you're stepping through the code like this. I mean, it's sort of similar, but not totally the same. Yeah, so I guess one thing I would say about this kind of zooming interface is it's more stateless. There's not a concept of the current line of code, but rather you see all of the state of the program, all of the history of the program as one gigantic visual that you can zoom in and out of and look at from various different levels of detail. Okay, so yeah, let's try to do this. Where should we start? I'm thinking, so here, so what I have here is basically dealing with first thing is I'm thinking about what should I first deal with, the while loop situation, or should I first deal with the function drill down situation. Both of them are things that I'll need to handle. Let's deal with the while loop situation first. And the two examples that I go to a lot are the Fibonacci sequence. You can implement the Fibonacci sequence in two different ways, either using a while loop or using recursion. So perhaps I will do that. Let me try it. So I'm gonna go back to my Playlang repository, and I think I probably already have Fibonacci sequence examples, although I don't see them right now. Okay, I do not see them. Do I have one here? I do have one here. Okay. I have one. This one is recursion based. So I'm gonna make fib recurse play, and that's this one. And I believe in here I can say run fib recurse, and it ran it, and it, I believe, also generated this history file. Yes, and that's the one I need to render the history of the program. I'm also gonna write a Fibonacci that's based on looping. Let me do that. I'm calling fib loop, and it's gonna be in the play programming language. It's gonna have a main function. I think I'm gonna model it after this one, only to implement the fib function differently. And I think I've done this once before, but I'm gonna just do it again. So I'm gonna have a loop counter, which is I, and I'll say while I is less than n, I is I plus 1. Maybe I'll do like a fib and fib next. Fib 1 and fib 2. How about that? Fib 1 is gonna be 1. Fib 2 is also 1. So and then inside here we do add fib 1 and fib 2 and store it in a variable. I'll call this fib next maybe, and then fib 2 is gonna be fib 1 gets fib 2 and fib 2 gets fib next, and then I think at the end we can sort of return the value of fib 1, and that's the answer. Maybe gonna try it. Fib loop. Oops. Okay. And my traverse function doesn't work for while loops. That's bad. So I'm gonna fix that. Basically, last time when I did the work for closure, where I needed to make a traverser, that code doesn't totally work for all the cases yet. So I'm gonna go into this AST while loop, and so the condition, a while loop has a condition and a body, and we'll want to traverse both of those. So condition traverse the body as well, note that body as well, and I'm gonna break. Hopefully that fixes it, and it does. It gives us 8, but we got a different answer for the other one, so perhaps it's like an off by one error probably. So maybe I need to maybe start this one at 1 or something. I don't know. Okay. Oh, this is recurse. Okay. That's that. I mean, I trust that works. Fib. What is fib of 7? 13, and we ask the recursive version should give us the same answer. And it did. Okay. So now we have both of these programs. Each one has a history file. So there's a fib loop.history and there's a fib recurse.history as well. Let's bring these files over to my Deep Zoom debugger project. And we'll use them both. I'm actually gonna get rid of these just so that I'm not confused, because I'm replacing them with these ones with different names. So put this one here. Oh, I actually moves the file. Okay, I have fib, and then I'm gonna move fib recurse history and fib recurse play over here. All right, and now I'm gonna use canvas to play with this. This is called, I'm gonna do fib loop first actually. Okay, so and the way I'm gonna do it is actually I'm gonna loop through the history array. So now I still have this guy running, this Deep Zoom debugger guy running. But currently it doesn't draw anything onto the canvas, it just prints out the history object. Okay, oops. There is actually a parser error. Oh, shoot. Closures undefined. I think that's a parser error on the part of the parser for the history file, not the parser for the program. I added this closures property to the stack, but there is a case when it's undefined, so I could fix that in the runtime code here to make sure it isn't undefined. Yeah, I've fixed this already too, so I kind of feel embarrassed about it. So if closures, if there is a closures, I'm gonna do new frame dot closures equals closures. If there isn't a closures, it's never gonna hear about this property at all. So let's try that again. Dang it, I'm gonna have to move this file back just to run it. So maybe I should not have moved it. I should have, okay, this time I'm gonna copy next time instead of moving. Okay, so I'm gonna come back to the Playlang project and run these two programs again, fib loop and fib recurse. And this time, hopefully, we'll get a history file that doesn't have closures that are undefined anymore. Okay, good. I'm gonna actually copy this guy this time. Copy. And over here, I'm gonna paste. Yes. Copy. Paste. Okay, for the history file, same thing. I'm gonna copy, paste. Ooh, it didn't want to read. replace the last one. Oops. So I'm gonna rename this one. It made a different version with a number. So I'm gonna delete the last history file. Yes, move to trash. And I want the fib recurse history file. Copy. Paste. Okay, so let's see if that worked this time. And it did. Okay, great. So these are the history entries of the program fib loop that play. Okay, so fib loop that play. What I'm gonna do is loop through every history entry and print out the line of that that line of code basically. So I'm gonna make a render function that would do this and call it, and then we'll say for let entry of history. For each entry in the history, I'm gonna the line number is entry.line, as we can sort of see. Maybe I should keep that printed out. Okay, so the line, we need the code. So I'll split the code into code lines. And then I think to index into the code lines, I'll subtract 1 byte because the line is not 0 index, but the array is 0 index. So this is the code number, line number, and then we have the actual line. And now I'm gonna render this line of code. Okay. I think I have to do some array index offsetting, but I'll leave that to the next step. So with the context object, I'm gonna fill text. Oh, I got a hint here. Line 0 pixel to 0, 0. I'm gonna fill it 0, 0. See what happens. Oh, there's the okay. I do see the code here. Sort of. And they're all layered on top of each other, so we should probably change that. We'll keep an offset. So this is X and this is Y. So Y is the one that we want to keep increasing. I have a line height. I have a code line height, and we also need to, I believe, set the text style or font, I believe. I think the font specification is gonna be something like normal, and then the font family. I'm gonna Google it. Canvas set font. So okay, the font weight, and then the pixel value, and then the font family. And the pixel value, I have this thing previously set up for this, so I'll use that many pixels, and that's the font family. And I also have this line height that I intend to use. Well, let's see what it looks like now first. Okay. So now I'm gonna use the array index, but unfortunately this for off syntax doesn't give us the array syntax, so we have to do this the classic way. We'll use a classic for loop with an I counter. While I is less than history.length, and then we'll grant an entry variable like that. And now we're able to say I times the line height, and that's what the offset should be for the height component. And there it is. Okay. That's cool. So this is sort of what this guy is doing, is saying that, let me think. This is not the recursion, this is a loop version. Okay. So this is every line that was executed. We started with line 15, which then the next line it goes into this fib function and executes line 2 and then 3 and then 4 and then 5 and then 6. Interestingly, it doesn't re-show this while line. It probably should, in my opinion, to show the fact that it needs to re-evaluate this conditional. So maybe I'll change the code, the programming language emission code, history emission code, to do that. It also doesn't show this line, which I'm thinking it might be helpful for it to show that line. Maybe. Because then I could just read this code. Like the loop has already been unrolled here, just naturally, because we're following the history of the code execution. And that's kind of nice, I would say. Okay, so let me think about that. I'm gonna take a short bathroom break, and then I'll be back. I'm gonna end this stream here and then start another one when I start.